In this video, I would like to discuss end of chapter question 6 from chapter 23 from the book Chemistry Cubed. I will just read out the question. Isoferrone is prepared on a large scale in industry for the use as a solvent in, for example, printing inks. A synthetic route to isoferrone is shown below. We see the synthesis scheme on the screen now. And first question is, give a reaction scheme to explain how substance 24 could be prepared from propanone. So this is actually the first reaction scheme. So the first question we need to answer, of course, is what's the structure of propanone. Propanone, the name suggests that's an alcohol based on propane. So it's a C3 body, 1, 2, 3, and a ketone. So this is just acetone in this case. So we need to prepare from acetone this molecule 24 here. And yeah, so you see at first a lot of new functionalities added. Somehow a carbonyl group is still preserved in our substrate. So we're having one group here. And what we also see is that there's a new double bond. And actually the double bond is conjugated to the carbonyl group here. So this is actually an enone. And this looks surprisingly like a component that can be done or can be synthesized from an aldol condensation. We can also highlight the bodies that are part of the product now. The first thing is these 3 carbon atoms here at the bottom that I highlight now in red are part of one acetone molecule, and the other 3 carbon atoms come from a second acetone molecule. And the bond here in the middle, the double bond, is actually the newly formed carbon-carbon bond that is formed during the aldol condensation reaction. And so with that we can directly see how this would proceed. So the conditions that we need to choose are now to transform acetone into the component 24 are basic, and then probably need to heat up a little bit to also eliminate the water. And to talk a little bit about the aldol condensation here for a moment, what we need are these alpha acidic protons next to the carbonyl group. The proton gets abstracted. We prepare an intermediary enolate ion. I can just draw that out for you here. So the proton gets eliminated gets abstracted by the base, and then we prepare something that looks like this. So we have a negatively charged intermediate here, and this negative charge can now attack again on another or not deprotonated molecule of acetone. We can draw that out here. So as we've seen numerous times in these exercises here already, we can directly see that this carbonyl atom here is partially positively charged, so it can be directly attacked by the electron density in our enolate ion here, and then we receive the initial or the first intermediary product from the aldol condensation reaction. And then that looks something like, let me quickly draw that here for you. It's actually this component. I just copied this. Oops. Draw or add a reaction arrow here to see how it looks. I remove the negative charge. Then this is the newly formed carbon-carbon bond, and now we just need to add the other molecules, the 2 methyl groups, and then also this former carbonyl oxygen, and this is of course negatively charged, and after some reprotonation basically we would end up with this intermediary carbonyl or beta hydroxy carbonyl component that we have also seen in the lecture. So this is our first intermediate here, and this molecule then can eliminate one molecule of water under basic conditions. This is not a problem, and then we end up with component 24, and this is the answer to the first question how this component can be synthesized from acetone. So to summarize this kind of question for this aldehyde condensation questions, is first important to realize, okay, where's the newly formed carbon-carbon bond between these between the starting material, then find where the alpha acidic protons are, and then proceed with the reaction scheme first from this beta hydroxy alcohol, and then eliminate water to get to this enone component here. Okay, so that was the first question. Second question of question 6 is draw component 25. We see that already on screen, and indicate all of the alpha hydrogen atoms. So yeah, that's a rather easy task. Alpha carbon atoms first are the carbon atoms that are adjacent to a carbonyl group. So actually this is the carbonyl carbon, and on the other side we have due to symmetry reasons, exactly the same carbon atom, and in direct vicinity we each see 2 carbon atoms. So in total we see 4 alpha carbon atoms. I can also mark them that this is nicely visible here. I will just do it on one side and then draw the hydrogen atoms on the other side so that it doesn't get too clunky here on screen. So we're having these alpha carbon atoms, and the hydrogen atoms that are attached to these carbon atoms are now so these alpha acidic hydrogen atoms here. So in total we see 5 alpha acidic hydrogen atoms next to each carbonyl group, and on the other side we see them as well. So in total we see 10 alpha acidic hydrogen atoms in alpha position. Okay, next question, question 3. Given that isoferrone is formed from 24, the structure that we have just discussed, in an intramolecular aldol condensation reaction, propose a structure for isoferrone. And I would like to combine this third question with the fourth question directly. Give a reaction mechanism to explain the formation of isoferrone from 25. So, what the question tells us is that isoferrone, our target molecule, is somehow formed in an intramolecular aldol condensation reaction. So this molecule reacts with itself in an aldol condensation reaction. And as we've also discussed initially, what we need to do to find out what's happening is basically first find the alpha acidic protons here. Luckily, the question already pointed this out to us. So we need to start with this material. I will just copy that so that that we can clean up the structure a bit. And now I'm just leaving one hydrogen atom, or one alpha acidic hydrogen atom, to basically keep it reasonably visible somehow, because it now gets somewhat messy. Okay, so what we do is basically we deprotonate at one of these carbon atoms, and then this formed enolate ion attacks the other carbonyl group on the other side of the molecule. And I can show you how this looks like. So first the deprotonation, let's remove this H and then add the negative charge here, and this negative charge will now attack the other carbonyl carbon atom here to close the ring structure. So we are having an intramolecular ring formation somehow. And as you can see already, is that there are 2 different positions here. So what we need to evaluate is which of these positions is first maybe more acidic, and second, which of these is potentially also the better ring structure to form. So this is the first thing that can happen, and the other molecule that is maybe formed is the deprotonation at this secondary carbon atom here, also at this negative charge, and then draw the reaction arrow here, something like this. Move this a little bit closer, and then we see the 2 structures that can be formed. Okay, first question to analyze. What is maybe the little bit more acidic hydrogen atom? The one on the methyl group or the one on this intermediary methylene group here? And we can see that actually this methyl group here is a little bit more acidic, because here 2 carbon, so here an additional carbon fragment or an organic rest, like an alkyl chain, is pushing a little bit more electron density onto the carbon atom. So actually, these carbon hydrogen sigma bonds are a little bit stronger. So actually, this methyl group here overall would be a little bit more acidic. But this is not the only reason that we need to investigate. The other thing that's important here is basically the ring size that is formed. And I can highlight the ring structure that is, or the carbon atoms that are then part of the ring for you here, so that it's clearly visible. So we use this carbon atom, 1, it attacks here, 2, 3, 4. And this would then be overall the ring that would be formed. So we see this is the first ring, so 4-membered ring. That's not so likely. Okay, we know in organic chemistry structures that have 4-membered carbon rings, but they are pretty they experience a lot of ring stress. And on the other side we see our carb anion that attacks 1, 2, 3, 4, 5, 6. So actually we can, in this case here, in the first case that we actually discussed, we can form a 6-membered ring. So this would actually be way more, be way better. 6-membered rings in carbon chemistry experience the least amount of ring strain. Of course, depends a little bit on the substituents here, but overall the 6-membered ring would overall be favored above the 4-membered ring here. And then we can draw the structure. So I just draw this up here. So we are forming a 6-membered ring, and then we need to draw the structure. So this is 1, this is then 2. So here we are having our alcohol group, and we are having another methyl group that's attached here. 3 has nothing. 4 has these 2 methyl groups that were previously in the center of the molecule. 5 is the former other acidic alpha acidic carbon atom, and on the other side here we see the carbonyl, or the former carbonyl group. And this is now how the ring gets closed. And yeah, what we don't know yet of course is this molecule eliminating water. We can probably assume that it is eliminating water. So in the last reaction step of this aldyl condensation reaction, we are again eliminating water. Let me add these reaction arrows here. We are eliminating water, and then we need to eliminate the water as well from the structure here, that it looks a little bit nicer. So, and this would then be our target molecule. So this would be actually the answer to the first question. This is the structure of isoferone, and then the answer to the second question, that is actually more part of this of the solution to this question, is this reaction mechanism. And 2 aspects here are important: the size of the ring that gets formed and the acidity of these alpha positions here. So when you are told that there's an intramolecular aldyl condensation happening, you always need to have these at least 2 carbonyl groups present, and then you can have a look which of these rings is more stable and experiences less ring stress.